All right, chemistry, let's take a look at the third portion of chapter 15, talking about neutralization reactions. What I want you to be able to do after this video, I want you to be able to explain the process of neutralization. I want you to be able to explain how acid rain damages marble structures, and define a Lewis acid and a Lewis base. This is going to be the last definition of acid and base that we introduce. So we'll have three. We'll have the Arrhenius definition, the Bronsted-Lowry definition, and then the Lewis definition. Lastly, name a compound that is an acid under the Lewis definition, but not an acid under the Bronsted-Lowry definition. Remember, Bronsted-Lowry definition of an acid or base is proton acceptor, proton donator. We need to be able to differentiate between Bronsted-Lowry and Lewis definitions. So let's get started. In aqueous solutions, neutralization is the reaction of hydronium ions, the H3O+, and hydroxide ions, which is the OH-, to form water molecules. A salt, remember in our first part of this, chapter, we said that any acid-base reaction is going to result in a salt and water. Now we're getting into it. A salt is an ionic compound composed of a cation from a base and an anion from an acid. So notice what's going on here. Here's our acid. How can I tell? Because this is the hydrogen that's going to be donated. This is the base because this is going to dissociate in solution to form an OH-. So we'll have an H+ and an OH-. Well, if you have those two things come together, you get your water over here. But after we've gotten rid of the hydrogen, after we've gotten rid of the hydroxide, we have Na, a sodium, and Cl, a chlorine together. Those will form an ionic bond, and you'll have, well, at least it'll be an aqueous solution, you have NaCl. That's a salt, right? It's a specific type of salt, but is a salt.
Hydrochloric acid is a strong acid that completely ionizes to form a hydronium ion and a chloride ion. Sodium hydroxide is a strong base which dissociates completely to form a sodium ion and a hydroxide ion. When these two solutions of equal concentrations and volumes are combined, the hydronium ion and hydroxide ion react to form water. The solution is neutralized. This equation can be represented as 1 hydronium ion plus 1 hydroxide ion yields 2 water molecules. The resulting solution is more neutral than either the hydrochloric acid or the sodium hydroxide.
Again, a neutralization reaction is anytime we have hydronium, or remember we said hydronium is kind of interchangeable with a hydrogen ion, but having hydronium ions react with hydroxide ions to form water. Acid, base, right? Low pH, high pH, neutral pH, neutralization reaction. Now let's talk about acid rain. This has actually become an issue since the Industrial Revolution. NO, NO2, CO2, SO2, and SO3 are gases that form from industrial processes, right? Big factories doing whatever they're doing are going to form these gases. But these gases can dissolve into atmospheric water to produce acidic solutions. So what do I mean when I say dissolve into atmospheric water? Clouds, water vapor, the moisture in the air. And from physical science, hopefully you remember that when you have a cloud, when you have water in the air, once it becomes cold enough, that water will condense, because when things become colder, their density increases, they compress. Once they compress enough, right, to a certain extent, they'll actually become dense enough that they can no longer float, right, for lack of a better word. And it will precipitate, it will fall out. It'll go from the gaseous state to the liquid state, and it'll fall as rain. But what if these other gases were dissolved in that water before it turned into rain, when it was still gas? And so we have this water that's supposed to be falling as rain, right? Clean rainwater. But what if it reacts with this SO3 either before it falls or as it's falling? When you combine SO3 and H2O, you get sulfuric acid, which is a strong acid. It's going to dissociate, right? You're going to have that acidic proton. any rain that has a high percentage of acidity, has a high concentration of this, which again is relative, is called acid rain. And acid rain can erode statues and affect entire ecosystems. So here you have this marble statue, this beautiful marble statue that's hundreds of years old. When exposed to acid, that marble is going to break down and slough off, and it's going to ruin these ancient statues. And so if you've heard about acid rain, it's a very big deal, and it's actually more common than you might think. Now let's get to our newest and last definition of what it means to be an acid or a base. It's the Lewis acid. A Lewis acid is an atom, ion, or molecule, any of them, that accepts an electron pair to form a covalent bond. So the Arrhenius definition of an acid was a something that increases the hydronium concentration in solution. Bronsted-Lowry acid was something that donates a proton. A Lewis acid is something that accepts an electron pair to form a covalent bond. This Lewis definition is the broadest of the three acid definitions. A bare proton, right, just a hydrogen ion, is a Lewis acid. For example, if we react the hydrogen ion, H+, with the ammonia molecule, and hopefully you remember from drawing our Lewis structures that NH3 has 3 hydrogens bonded to the central nitrogen, but it also has a lone pair of electrons. That lone pair of electrons is going to be accepted by this positive charge here. And so what happens is, and this is a really bad representation right here, so we're not even going to pay attention to this. This is representing a coordinate covalent bond or a complex. The positive charge of this is attracted to the negative charge of this lone pair of electrons on the central nitrogen, and so we get an ammonium ion. The formula for a Lewis acid need not include hydrogen. It doesn't have to have hydrogen. Remember, when we talked about acids before, as a proton donator, so it's got to have a proton to start with. When an Arrhenius acid raises the concentration of hydronium in solution, it's got to do that by having hydrogen in it. But a Lewis acid doesn't actually have to have hydrogen. Okay, so that's a big distinction here. For example, the silver ion can be a Lewis acid. So in the exact same way that we showed on the last slide, but with Ag instead, Ag+, well, here is our two electrons, a lone pair from ammonia, right? There's going to be a coordinate covalent bond, right, between this silver and the ammonia, and we're going to have silver with bonded to two of these ammonias, right? That's why we have this weird representation. This is an NH3 on this side, NH3 on this side, because we're bonding two NH3s. Okay, you guys following that? Central silver, ammonia on this side, ammonia on this side. This weird symbol represents the covalent bond that's occurring between them. So any compound in which the central atom has 3 valence electrons and therefore forms 3 covalent bonds can act as a Lewis acid. Boron, main group 3, therefore it has 3 valence electrons and can form 3 covalent bonds. Here's Bf3, right? We can react that with the fluoride ion, right? F minus, remember this G with the weird hat is supposed to be a minus sign, so this is the fluoride anion. We can react these two things in solution. We will have Bf4 with a minus, right? Because what have we done? We've accepted electron pairs. Where was the electron pair from? Right here, right here. And this electron pair is satisfying, it's fulfilling an octet of electrons for the boron, which would normally only be filled with 6 electrons. Now it can go up to 8, getting that noble gas electron configuration. So here are our definitions so far, and this is actually going to be the end of our chapter, our chapter on acids and bases. We have the Arrhenius definition of an acid. So anything that increases the concentration of the hydrogen ion or the hydronium ion, remember they're interchangeable. So if you hear one professor talk about H+, another one talk about H3O+, they're not disagreeing with one another. It's just different conventions. They're actually talking about the same thing. An Arrhenius base is anything that produces hydroxide anions. Bronsted-Lowry acid, on the other hand, is donating H+, donating hydrogen ions, donating protons. A Bronsted-Lowry base is accepting those protons, accepting those hydrogen ions. But the Lewis acid is an electron pair acceptor, anything that is going to accept an electron pair, whereas the base is anything that is going to donate the electron pair. All right, guys, that's going to do it for the video lecture for Chapter 15. Stay tuned for some practice questions.